Okay, now we're going to take a look at something that you're probably very familiar with, but maybe looking at them in a different way. As long as you've been doing algebra and calculus, or not all of you have made it to calculus, but you've been studying functions, and you're probably used to the f of x notation that you've seen. We're going to take a little bit of a more general definition of a function and think about it as a mapping. Really, a function is a mapping of elements from one set called the domain to elements in another set called the codomain. Now, you're probably used to range. The range is actually the actual numbers in the codomain. You can think of this as range, but there's a slight technical difference between range and codomain. But a function is a mapping of elements from a domain to a codomain such that every element in the domain is mapped to exactly one element in the codomain. So this first mapping over here, we could call this first circle the domain, and we can call this second the codomain. And you can see that everything in this domain goes to exactly one value in the codomain. Now, when we look at this first value in the codomain, it's okay that two different x values are producing the same y value. Okay? But over here, what we have, I'll highlight these arrows in blue, the first value in the domain is actually producing two different values in the codomain. And that's a problem, right? A function needs to be predictable. Every time you give it the same input value, it has to produce the same output value. Now, different input values can produce the same output value, but you can't have an input value like this giving out one answer sometimes and a different answer other times. Okay? So you've probably learned how to tell whether something is a function or not. You may not have used this sort of set idea. We could think of these circles as sets like we did with Venn diagrams, and the dots are elements in the set. You're probably used to doing a more visual check of whether or not something is a function, and then we use something that we call the vertical line test. Okay? The vertical line test, which is often abbreviated VLT, right, basically makes sure that every x is only mapped to one y. If any vertical line hits the curve more than once, then that one x value has two y values associated with it and will not be a function. Okay? Now, in this case, even though this one vertical line only hits the curve really once, all the other ones hit it twice. So at any of these particular x values, you're not sure which y value it's going to spit out. Sometimes it'll spit out the positive one, sometimes it'll spit out the negative one. So we would say this one over here is a function because it passes the vertical line test. This one is not a function because it fails the vertical line test. Okay? So that's all considered review. What we're going to look at and focus on more, which you may also be review, is the idea of a one-to-one function. One-to-one functions are important in a lot of areas of mathematics because a one-to-one function can be used backwards. We can find the inverse of it. Okay? A function is one-to-one if every element in the codomain, that's the output, corresponds to exactly one element in the domain. Okay? So the idea is everything here only associated with one unique value over here? And you can see this particular value here has two different x's generating the same y. Now, this is still a function, right? But this one we would say is not one-to-one, right? Which a lot of times you'll see just abbreviated as the number 1-1, okay, one-to-one. Okay? Because of this here, you have two different x values giving you the same y value, no outputs repeated. That's sort of the easy way to think about this. This output value is repeated for two of these input values. Now this one over here, this second example, every one of these y values or output values only comes from one unique value. Okay? Now the graphs below, we have a similar situation. There's a way to figure this out with a nice easy test, but here we would want to use what we call the horizontal line test. Right? We want to make sure, horizontal line test, we want to make sure that what we're looking at as a y value only comes from one x value. Right? So if we start drawing horizontal lines through here, any horizontal line that hits us more than once means that that same y value is associated with multiple x values. So this one would fail the horizontal line test, whereas a function like this, even though it levels out for a second, this would pass the horizontal line test, and therefore this kind of function would be one-to-one. If I know the y value, I can go backwards to get the x value. In this case, if I knew this y value, I wouldn't know which one of these three x values came from. Okay? So one-to-one should be easy sort of visually. What I think may be a little bit of a challenge is how do we do it algebraically? So the more formal definition for f of x is one-to-one. F of x will be one-to-one if we have the following. If f of x equals f of y, it means if we have the same y value coming from two different x's, then really those two x's can't be different. They have to be the same. So if f of x and f of y produce the same output, then it must be shown that x actually equals y. Okay? So let's go ahead and see how we would put that into practice for a couple of examples. For this first one, we have a function f which maps r to r. That means a real number to a real number. F of x is defined to be x squared minus 3. Okay, now if you think about what a picture looks like, you could always draw the picture and sort of get a sense as to whether or not this is going to be one-to-one. But what we really want to do is figure out how to do this algebraically. So f of y equals y squared minus 3. Okay? Now what the definition says is if f of x equals f of y, we're going to do this as a direct proof. So we're going to assume that x squared minus 3 equals y squared minus 3. And then we're going to have to show that x has to equal y. Okay, so we're going to try to solve this algebraically. We'll add 3 to both sides. Okay, we get x squared equals y squared. And it might be tempting to just take the square root on both sides. But if x squared equals 9, remember that x is really the plus or minus square root of 9. Right? Because both positive 3 and negative 3 would produce 9 as a square. So you have to use what we call the square root method. Right? And once you see that x has two different answers, right, you know that this is not going to be one-to-one. There is no unique y value. X could be negative y. You could have two different inputs. You could have y and negative y both produce the same output value. Okay? Now for the second example, if we let g of y equal 5y plus 7, and then we set 5x plus 7 equal to 5y plus 7, again, trying to solve here, right, we get 5x equals 5y, and when we divide by 5 on both sides, we get x equals y. Therefore, if we assume that f of x equals f of y, we come to the conclusion that x equals y. Therefore, g of x is one-to-one. Right, I'll just be complete here and say f of x is not one-to-one. Okay? So we're going to do this as a direct proof. You said f of x equal to f of y, and then we show that x equals y. Okay, we've got one other way to classify functions besides one-to-one. We can talk about a function being onto. A function is onto if every element in the codomain corresponds to at least one element in the domain. What this really means, in simplest terms, is every possible output value is reached by some input value. So if we look at this first example over here, right, this bottom value sitting in the codomain doesn't have any input values in the domain that generate it. So we would say that this one is not onto because there's an unreached value in the domain, a codomain, sorry. In a case like this, every single one of these, in the second example over here, every one of these output values is reached by at least somebody. It doesn't matter that this bottom one is reached twice. Right? That would prevent it from being onto, from one-to-one, but it is, in fact, onto. Okay? Now, I wanted to mix these up a little bit here just so it wasn't automatic here. Let's think about whether or not this is onto or one-to-one. Okay? In order to be onto, every single y value is going to have to be reached at some point. And if we understand that this arrow on the end means this function goes up forever. This arrow on this end means that function goes down forever. There's no breaks anywhere in the y-axis where we can't look left and right, left or right, and see the function somewhere. So we would say that this is onto, because no matter where you are, you can always get to the function. Right? No matter where you are, you can always get to the function. You could sort of think about the shadow that the function is leaving on the y-axis from either side. Now in a case like this second one over here, this upside down parabola, you can see there's a bunch of values up here that never get reached by this function. So these are unreached, and we would say this is not onto. Right? These are unreached y values. Okay? So again, it's important to understand the concept visually, but then what we have to be able to do is also think about this algebraically when we have function definitions. So the way we're going to think about this for functions, f of x is onto. If y is in the codomain, there must be some x in the domain such that f of x equals y. So let's take a look at these two examples. This will be a little bit easier than the one-to-one examples. Sometimes you have to just do this by exploration. F of x equals x squared minus 3. Okay? Are there any y values? Right? Are there any restrictions on what x squared minus 3 can do? We know that x squared is always greater than or equal to 0. Right? That means that x squared minus 3 is always greater than or equal to negative 3. And just subtract 3 from both sides. So what that means is anything below negative 3, like x equals negative 4, can never be, y equals negative 4, sorry, right? Can never be reached. Okay? How would we show that? Let x squared minus 3 try to reach negative 4. If you add 3 to both sides, you would have x squared equals negative 1, right? X is not a real number. Okay? So we would have to conclude that this function is not onto. On the other hand, if we let y equal 5x plus 7, okay, you can subtract 7 from both sides here, divide by 5 on both sides, and you know that x is y minus 7 over 5. Any y you want to reach, if you want to reach a particular y, all you have to do is subtract 7 and then divide by 5, and that will generate the x that would generate that y. Okay, so we can say here that you're onto because we can find an x for every y. Okay? Sometimes for onto, you really have to have a sense as to whether it is or it isn't. If it isn't, you're kind of looking for a counterexample, whereas if it is, you just solve for x. Okay? So give these a try, see how you do, and practice some homework.